Bernoulli theorem for the Bernoulli equation. So when we discuss the Bernoulli theorem, we refer to that when incompressible and non-viscous liquid flows in streamline, that is between 0 and 1000, must be the flow, that is the stable, from one place to another, then energy point of its path, total energy per unit volume, that is sum of the pressure energy, kinetic energy and potential energy. P stands for normal pressure, half rho v square, that is kinetic energy, and rho gh, that is potential energy. Sum of all the three energies will be constant because energy is neither created nor destroyed according to law of conservation of energy. In the above equation, rho gh is called static pressure and half rho v square is called dynamic pressure because the dimension of each term are same as that of pressure. Now for a unit mass, Bernoulli equation can be written as, well, the Bernoulli equation is P over rho plus half V square plus G is equal to constant, and for a unit mass, M must be 1, so this equation has come. Bernoulli theorem is also law of conservation of energy for the following liquids. If the flow of liquid is on the horizontal surface, then height will be 0, there will be no height, and we add P and half rho V square, and that is equal to constant. Therefore, for a horizontal streamline motion, the sum of the pressure and kinetic energy per unit volume at every point of the liquid is constant. It is clear from Bernoulli theorem that the flowing liquid, where the velocity of flow of liquid is less, the pressure is larger there, and where the velocity of the flow is greater, the pressure is smaller. If the liquid is allowed to flow in such a tube which is narrower in the middle, then the velocity of the liquid is greater in the parts and the pressure is smallest. When a liquid is allowed to flow from broader pipe to narrower pipe, the pressure reduces. Deep water is always calm because the static pressure of deep water is quite large. So the velocity of water there will be very small, only in the deep water. Now we come towards the application of the Bernoulli theorem, that is the construction of the airplane wings or otherwise in the various concepts like in the Bunsen's burner, which we are using in the lab. Then second is atomizer, that is a sprayer. Then comes the filter pump, where the water is filtered. In all these cases, Bernoulli theorem is applied. Ball placed on a water fountain begins to dance and blowing off a tin roof. These are all the examples of the Bernoulli theorem because in all these cases, certain pressure is made at the end of the device. Now, Magnus Effect. When a tennis or cricket ball is thrown spinning inside of moving in a straight line, it moves along curved path. This is called swing of the ball, and the whole thing is known as the Magnus Effect. Now we come towards the shapes of the wings of the aeroplane. The shape of the wings of aeroplane is so designed that the curvature of its upper surface is greater than the curvature of the lower surface, and its front end is shaped round while the back end is flat. Now next example is a venturi meter, in which the tube at the middle is of the low diameter and extreme tubes are of the greater diameter. When the water will rush up in the tubes of greater diameter, its velocity will be less, but when it is flowing in the middle part where the radius of the tube is less, the velocity of the flow will be more. So it is shown in the figure here. V1 and V2 are the two velocities. A2 is the area, H is the height. So now it is a device by which the rate of flow of liquid can be determined. Rate of flow of liquid, that is the volume of liquid coming out of the tube per second. That is given by formula Q is equal to A1 A2 under root 2 GH over A1 square minus A2 square. Therefore, the rate of flow of liquid is proportional to the square root of H, which is difference of the levels of liquids in vertical tube. Now, velocity of efflux. Now we come towards the velocity of efflux and the Torricelli theorem. Now, what exactly we are finding in the figure, that there is a container in which the water is up to height h, that is the capital H, and at height small h, there is an orifice or a hole. Water comes out of the hole and it is coming out of the hole falling on the ground. So its trajectory is less and the range will be x. But now we come to a lower point P, its height from the top will be more, and we find that it will make a curve larger than the first one. And in the third case, we will find that the hole is at the bottom at height h. Again, the range of water will be less. So in case of point A and C, the range will be less, whereas in B, the range will be maximum. This is what interpreted in the velocity of efflux. Let the vessel be filled with liquid up to height h, and there is an orifice at A, which I have spoken earlier, at the depth h, below the free surface of the liquid from which liquid is coming out. The velocity of efflux of the liquid coming out from the orifice is V. The pressure of the free surface of the liquid and at orifice are same, equal to atmospheric pressure, that is P is equal to H dg or 1 atmosphere or 76 centimeters of mercury. Therefore, there will be no effect of atmospheric pressure. The kinetic energy of the surface of liquid is zero, and so there is only potential energy. The liquid coming out from the orifice has both potential and kinetic energies. From Bernoulli theorem, the sum of the pressure and total energy per unit volume of the liquid must be same at the free surface of the liquid and at the orifice. Therefore, P plus 0 plus RGH will be equal to P plus half rho V square. Rho is for mass over volume and Rg into H minus H. So we got the expression half rho V square is equal to rho GH. The formula is called the Torricelli relation. The above all formula were derived by Torricelli, and hence the relation is known as the Torricelli relation. We know that the velocity of the body falling freely from the rest from a certain height is given by function v is equal to under root 2 gh. Therefore, the velocity of efflux of the liquid from an orifice is equal to that velocity which the body acquires is falling freely from the height h. Liquid flows along parabolic path after coming out of the orifice. Time taken by liquid in falling from orifice to the ground is calculated by function twice of h minus h whole divided by g. The range of liquid x, so range of liquid x is equal to horizontal velocity into time, or it is under root 2 gh into under root twice of h minus h over g after all cancellations, and we will do rationalization of 2h minus h, and we will come to the equation 2 under root h into h plus h. Now next point is whether the orifice in the vessel is at depth h or at depth h minus h from the free surface of the liquid. At the highest h from the bottom of the vessel, the emerging liquid will fall at the same distance that the range x of the liquid will remain same. X is called the range. If h is small h is h over 2, that is orifice height is half of the height of the liquid filled in vessel, then the range of the emerging liquid will be maximum. That is, the stream of liquid will fall at a maximum distance. Therefore, for h, we can replace h by 2. So, we will find the value of range x, and that is twice root of h over 2 into h minus h over 2, that is 2h minus h, that is again h over 2. So h over 2 into h over 2, whole the thing will become equal to h. The range of the system of the particles, the range of the stream of liquid will be equal to the height of the liquid vessel or liquid filled vessel in it.